So welcome everybody. We are very happy to have Heather Lee with us today. And she will be telling us about global homological mirror symmetry for genus 2 curves.
Okay, thank you very much for the invitation to speak here. And I will present the joint work with Haniya Azam, Catherine Cannizzo, and Chiu-Chu Melissa Liu. This is still a work in progress, and we are hoping to finish writing up in the next few months. So to begin with, here's a picture of Catherine Cannizzo's thesis result. And let me talk through each component of this picture. So she proved a homological mirror symmetry result for genus 2 curves. Here I'm denoting the genus 2 curve as theta tau, and tau is the complex parameter of the genus 2 curve. We know that the complex parameters for genus 2 curves live in this three-dimensional space. That is the Siegel upper half space given by symmetric 2x2 complex matrices, such that the imaginary part has positive determinant. In Catherine's thesis, she considered this one parameter family of complex structures. Most of her thesis can be directly extended to cover all complex parameters, but a couple of new ideas are needed, and I'll point out in this talk where the new ideas come in. So a genus 2 curve can be thought of as a hypersurface in its Jacobian variety, which is a abelian surface, a 4 torus. And this hypersurface is defined by this Riemann theta function. So I know we've barely started talking about this picture. But at this point, if you're wondering about higher genus surfaces, in general, for genus G surfaces, their Jacobian varieties are of dimension 2G. So just looking at the dimensions, only in this genus 2 case is a hypersurface in its Jacobian variety. One can certainly embed higher genus curves as hypersurfaces in something 4-dimensional, a lot of things, but there's no this kind of uniform way of incorporating all complex structures to study global mirror symmetry, as we vary the complex structure in this entire complex moduli space. In another direction of generalization, we are actually writing another paper on hypersurfaces in abelian varieties of any dimension that's perhaps more focused on the monodromy computation that we'll talk about later than mirror symmetry. So, so continuing this picture. So as a multiplicative abelian variety, this V tau can be defined in this way. So V tau is just a C star 2 quotienting by this tau times Z2. So the action of an element tau times n, n in Z2 is given by this formula. So so tau times n acts on x1, x2 in C star 2 in this way, just yeah, according to this formula, and that gives this abelian surface. And so in case anyone wants to think about additive abelian surfaces, this is equivalent via the exponential map to the C2 quotiented by a lattice, Z2 plus tau Z2. And so now you can see that this is a 4 torus. It's a C2 quotiented by lattice. Visually, when I think about this, I like to just think about the 2 torus, which is similarly defined, like with 2 torus is C quotiented by a lattice. So, so here we have this genus 2 curve, and that's embedded in this 4 torus. And the pullback of this embedding gives a functor from the derived category of coherent sheaves on the abelian surface to the category of coherent sheaves on the genus 2 curve, just by this functor just takes a line bundle on the abelian surface and restrict it to a line bundle on the genus 2. So, so Catherine's thesis is actually a cohomology level result currently, not a infinity level. And she considers coherent sheaves generated by powers of ample line bundle L, for which so this for this line bundle L is the line bundle for which the theta function is a holomorphic section, gives a holomorphic section of L. So, and this vertical arrow is the homological mirror symmetry statement for abelian surfaces, which was proved by Fukaya for abelian varieties of any dimensions. And here we are looking at complex dimension 2. In the one-dimensional case, which is the elliptic curve, this was shown in the 90s by Polytope and Zaslow. Like I mentioned earlier, I still just use the one-dimensional picture to visualize what's going on in dimension 2 or higher. So, so when I think about abelian variety, it's just a square that's quotiented by like a parallelogram, like a C2 quotiented by lattice, or yeah. So, okay, so now this mirror symmetry statement says that the mirror of a 4 torus is also a 4 torus with the this complexified Kähler structure matching matching this complex structure. So so this part, the imaginary part, would be the usual symplectic structure, the real symplectic structure, and then there's a B field. And yeah, so so if we write this symplectic structure using this moment map coordinate, just by defining, so this is in the complex coordinate, and so if you write it in the so this coordinate is just the coordinate on this R4 quotient thing Z4. There's a 2 component of rho and 2 component of theta. And if you write it in the moment map coordinate, C, and the symplectic form here is just dc d theta. Okay. So under mirror symmetry, this line bundle L will correspond to this linear Lagrangians of, so each of the powers of this line bundle Lk will correspond to linear Lagrangians of slope k. So so I'm still in my head picturing this. The abelian surface is a square, like a torus, and here's a line of negative slope k. And so I was debating about when, so there should be like a factor of 2 pi with the thetas to make the formula consistent with the formula I'll write later on in the talk. I was debating whether to put it there or not, since adding all the 2 pi's makes it messy, but then I kind of left it out. Now I'm wondering if I should have put it in for accuracy, but there should be like a 2 pi with the theta component. Okay, so so that's this arrow. So the genus 2 embeds in a abelian surface, and that's mirrored to this 4 torus. And now this one, so the mirror for the genus 2 curve can be constructed based on the generalized SYZ Strominger-Yau-Zaslow philosophy. And for hypersurfaces in toric varieties, this generalized SYZ mirror symmetry is worked out by Abuzed, Aru, Kazakov. There's a section in their paper that also explains hypersurfaces in abelian varieties in this SYZ construction. So on the genus 2 curve, we can't have a global Lagrangian torus fibration. We can certainly have S1 fibration for part of it, but then we get to a singularity when we reach the pair of pans at the joints. So in this paper by Abuzed, Aru, Kazakov, they identified the hypersurface, things like this, with a 3 complex dimensional manifold. That's this blow up. Is the hypersurface cross 0 in V cross C. So so in this 3 complex dimensional on the 3 complex dimensional manifold, there is a Lagrangian T3 fibration that we can discuss as SYZ mirror symmetry. And then they get this mirror Landau-Ginzburg model Y. So this is so this Y is a there should be a tau, so Y tau. So this Y is a toric Calabi-Yau threefolds, and there's this superpotential to C. So, this is a symplectic fibration with a singularity at 0. So this superpotential is a function that vanishes to order 1 on each of the toric divisors of Y. So Y has a complex T3 action on it, and the superpotential is equal to the 3rd complex toric coordinate. So we can talk about this Y and the superpotential more explicitly soon. Right now, to visualize it, we can take a look at this picture. So this is the symplectic fibration Y to C, and the generic fiber of Y is, each generic fiber is a T4 that is actually isomorphic to the mirror of the abelian surface. And there's a singular fiber above 0, and the singular fiber looks like this. So this I'm drawing a moment polytope for CP2 blown up as 3 points. And then there's a group action on it. And this group action on the mirror depends on the imaginary part of the complex parameter omega. So so if I just draw the hexagon, that's CP2 blown up by 3 points, the moment polytope of it. And then this group action identifies the opposite sides. So we get something that looks like this as the moment polytope. And the critical locus of the superpotential is the boundary of this polygon. The moment polytope of the critical locus is the boundary of the polygon, and you can see that is 3 lines with three circles. So so the critical locus, so each of this line segment is a sphere. So the critical locus looks like this banana configuration, consists of 3 spheres. And this three-dimensional, there are 3 degrees of freedom that are given by the symplectic area of the 3 spheres. That's going to match with this 3-dimensional space given by the imaginary part of the complex parameter. We'll talk about how they match later in the talk. So in Catherine's thesis, this complex parameter was chosen so that on this side, the 3 spheres have the same area, and that gives a 1 parameter family. And here we would like to have 3 parameters that are freely varying. So I think she in her thesis, she had a symplectic structure on Y that was constructed depending on this symmetry that she had, that the 3 spheres had the same area. And now to allow them to vary, we have to use a different symplectic structure. So that's one of the new ingredients in our work. So, and now let's talk a little bit more about how this Y is explicitly constructed. Oh yeah, sorry. Yeah, so let's first complete this picture. So there's this genus 2 embed here, and the pullback of the embedding gives a functor from Lagrangian's powers of this ample lamp bundle restricted to lamp bundles on the genus 2. And the lamp bundles corresponds to Lagrangians on the mirror for torus. And this 4 torus turns out to be isomorphic to all the generic fibers of the mirror to the genus 2. And then this this map here is we take a Lagrangian in a fiber above this minus r radius r, and then we parallel transport it along a U-shaped curve in the base. So ULK is denoting a Lagrangian in the total space that's taken from this Lagrangian LK parallel transported along this U-shaped curve. So there's a fat Lagrangian in the total space that maps here. So and then Catherine showed that this diagram commutes, and that proves a homological mirror symmetry statement for the genus 2 curves. And now let's talk a bit more about how this Y is constructed. So this work by Abuzid, Arul-Kazakov gives way to construct mirror for hypersurfaces in toric varieties, in particular in C star 2 that we want. So, so this genus 2 curve is a hypersurface in this abelian variety, abelian surface. And so here, yeah, I forgot to quotient. So there's a quotient. So this would be a hypersurface in C star 2, and then it's quotiented, and then but the pre-image under this quotient, we call it theta delta. So under this pre-image, we have a hypersurface in C star 2 defined by this Riemann zeta function. And C star 2 maps to a log R2 by this log map. And if you look at all these formulas and take a closer look at all the formulas, you see that this V tau maps for this diagram to commute, this V tau maps to R2 quotienting by the imaginary part of tau times Z2. Okay. So So the first line of this diagram, we can follow this opposite or Rule-Kazakov construction to construct a mirror. So here's a formula for that gives the moment polytope of the mirror to this theta tilde, and then we can quotient this by this action, this omega times Z2 to get a moment polytope for Y. Okay, so what are these formulas? So the C coordinate is here, is given by this map, which is on the C2, and then so the moment polytope is three-dimensional. So that you take the C coordinate and introduce a third eta coordinate, and this eta coordinate needs to live above this function of C, and this function is the Legendre transform of this minus kappa function. So I think some of you in the audience are familiar with this, but basically what this is we obtained by looking at this formula, but especially by looking at the exponent of this formula. Yeah, so kind of because going from X to C, we take the log map. So we are looking at the exponent of like the X term and so on. So if you look at the exponent of this formula, in this formula is an infinite sum indexed by n in Z2. So that's why here we have infinitely many functions in this collection. And this takes the maximum of that. So each one of this expression would be exponent of X here if we replace of C here, if we if we look at the exponent of C and this function here. So yeah, so the exponent is C, sorry. Yeah, so if we take the log map and we look at the C goes on the exponent. So anyways, I don't want to dwell on this formula since I'm now going to explain this work as the focus of this talk. But the point is, we look at the exponent of this formula, and for each term, we get the expression here. So there are infinitely many terms. So for one for each n in Z2. And then we get this as the moment polytope. And this moment polytope has infinitely many facets, one for each n in Z2. And what the moment polytope looks like is there's one for one facet for each n in Z2, and that facet is defined by this function Ln equals to 0, and Ln is given by this formula. And this facet is normal to the vector -1, -n1, -n2, and 1. So you can imagine that this is a three-dimensional polytope. So imagine a three-dimensional ball, and then the surface of the ball, the boundary, like the bottom of the ball, has infinitely many facets, one for each n, and each facet is normal to this vector. And then this coordinates, so this coordinates in this polytope satisfy this relation with respect to elements in this quotient. So take omega m in Z2, it acts on the coordinates in the polytope in this way. So then using this, we can quotient this moment polytope for y tilde near the singular fiber of this superpotential and to get a moment polytope for y. So so this gives a description of what the moment polytope looks like, but we can give a more explicit picture. So there are going to be 4 cases. So I put here a lot of pictures and a lot of formulas, but you don't have to worry about the details so much. So basically you can calculate what this polytope is. And that depends on the omega. And remember that omega to begin with was the complex structure, the imaginary part of the complex structure of the abelian surface. And that factors into this in how the mirror looks. And so depending on this parameters of the omega, what kind of criterion they satisfy, there are 4 cases. And we can also calculate and see that each of the facet is a hexagon. And then by changing omega, we just kind of change how the hexagon looks. So so basically here, oops, sorry. We take the so this hexagon I'm drawing is a hexagon, is a facet that corresponds to the 0, 0 facet. So the facets are all labeled by n in Z2. So in the middle here, there is a facet corresponding to the 0, 0 facet. And if you calculate and look at which other facets are adjacent to the 0, 0 facet, there can only be like 8 different possibilities. There can be 0 plus minus 1, or plus minus 1, 0 facet, or plus minus 1 minus 1, or plus minus 1, 1. So there are 8 potentially adjacent facets. But then if you calculate them depending on what the parameters satisfies, the inequalities that the parameter satisfies, as you can see in all these cases, only 6 of them is adjacent for each case. So so in this picture, the 1, 1 facet, in this picture, the 1, 1 facet isn't adjacent, but in this picture, the 1, 1 facet is adjacent, but the 1, 1 minus 1 facet is not adjacent, and so on. So there are roughly 4 different configurations, and then there are also 3 intermediate degenerate configurations in between these 4. Most of this is kind of a bookkeeping, but it's kind of interesting to see this translation phenomenon happens as the parameters omega vary. And this dotted parallelogram is the lattice, the gamma b, the omega lattice, the omega Z2 lattice. So here in the parallelogram, we have a fundamental domain. And so just to show you an example of how the hexagon varies as the parameter omega changes. So here is an example of, that's well known, is an example of a TF-flop. So here, suppose we take this to be the imaginary part of our complex structure and of the abelian surface. And now we construct the mirror and everything. And then we see that this imaginary part, like we've been saying, it factors into the geometry of the mirror. That so here we are going to have a hexagon, that the hexagons that looks like this. So remember, all these tails are the bottom of the ball, the 3-dimensional ball. That's the moment polytope of the y tilde. And here, if we let omega be this, we are going to have hexagons of symplectic area 1 here. So of the side length 1 here, that's going to correspond to the symplectic area of those three spheres in that 3 banana picture. So 2 of them have the same area, but 2 of them have the same area. But for 1 of them, the area is changing. Is this lambda parameter that we are going to change. So as lambda goes to 0, you can see that this side of it disappears. So we just, the hexagon becomes a square in this degenerate case. And then as lambda becomes negative, and we still take this to be the parameter matrix, the imaginary part of tau, the hexagon kind of shift into a different configuration to this. And the side length of the hexagon is completely determined by this omega, using based on all these formulas that one can calculate. And we see that just using these formulas now, when lambda is less than 0, the side length corresponds to lambda in a way that 2 of the sides are 1 plus 2 lambda, and then the other side is minus lambda in length. Okay, so this kind of shows a transition of how the geometry of the mirror changes as we vary the complex structure on the abelian surface that the genus 2 curve is embedded in. Okay, so now maybe it's a good, yeah, so if you have any questions, feel free to interrupt me. So for the rest of the talk, I'm just going to kind of focus on the symplectic structure on Y and the monodromy computations. So,
hi, Heather, I have a question,
yeah.
just a quick question. That so your lambda, is your lambda some kind of symplectic area? So what does the minus lambda mean?
Oh yeah, because when lambda is negative, the area needs to be minus lambda.
Oh.
Yeah, so here, sorry, it got messy. So the this omega was the imaginary part of this parameter, the complex structure on the abelian surface that the genus 2 is embedded in. But this omega factors into the how we constructed the mirror, what the geometry of the mirror is. And then just by kind of looking into the details of this formula, we can get the hexagons, and then we can see that the omega corresponds to the side length of the hexagon in this way in the various cases. So basically this transition happens by transitioning, going from case 1 to case 2. So so in case 1, the omega and the side lengths, which corresponds to the symplectic areas of the 3 spheres, are given by this identity, and then in this case is given in this way. And so then we have here when lambda is less than 0, the side length of B1 is like minus lambda, which is positive. Yeah.
Oh, okay.
Yeah, and then this 1 plus 2 lambda is like less than 1. So this one looks smaller, kind of.
Okay. Yeah, thanks.
Mm-hmm. Yeah, thanks for the question. So so there's a lot of formulas. Let me talk through. So there's a symplectic structure on Y. And so this was kind of already readily set up for us. We just realized that if we use Guillemot's Kähler structure on toric varieties, just adopt that, it works for our for everything we need. So so I think in the 90s, Guillemot constructed Kähler potentials. Actually, even before Guillemot, people know how to construct symplectic structures on compact toric varieties, to construct toric invariant symplectic structures on toric varieties via this symplectic reduction. And Guillemot Guillemot's work gave all these potentials, the Kähler potentials for those symplectic structures. So this symplectic structure is just constructed via symplectic reduction. But for us, on this Y tau, so we're going to construct the symplectic structure on the Y tilde. So the Y tilde was the pre-image before the quotient. And so that's going to be like a surface of like a manifold of infinite type. You can see that the moment polytope of Y tilde has infinitely many facets, one for each Z2. And on Y, that's all quotiented. So you just look at the fundamental domain. But we're going to put a symplectic structure on the Y tilde. Actually, not the entire Y tilde, but only for this mirror symmetry picture. We really only need a small neighborhood of the singular fiber. So we're gonna put a symplectic structure on a small neighborhood of the singular fiber. And that singular fiber corresponds to like the facets of the moment polytope. You can see that the facets are the hexagons. So that's what the singular fiber looks like. So on a small neighborhood of Y tilde, there's this work by Cannizzo, I think recently, a few years ago, that that kind of used the idea of Guillemot, but they made it work on this infinite dimensional manifold. No, not infinite, sorry, manifold of infinite type with infinitely many facets. And then there's the group action, and they show that the symplectic, the Kähler potential you put there, you can descend to the quotient with respect to this group action. So what is Guillemot's Kähler potential? So on Y tilde, we can have a Kähler potential. So this is a potential. So it's just a function defined on the actually just the moment map coordinate. So on Y tilde as a toric manifold, we have an action angle coordinate. And so this potential actually just depends on the action coordinates on the C's. So the eta is the third coordinate of, so C and eta are the coordinates on the moment polytope. And Guillemot, so for compact toric varieties, Guillemot had this potential that doesn't have this chi function in there. So if you ignore this chi function and sum over all the toric facets of a compact toric variety, and just sum over all the facets of this part, that would be the Guillemot's potential. And you can see that this potential function entirely depends on the combinatorial structure of the moment polytope. So because this L function here is this function L. So if we know what the moment polytope looks like, we can immediately write down this function. And now with the infinitely many facets, what Cannizzo did in their work is to have this indicator function chi. So what this function is we have an open cover on the polytope. So suppose we have an open cover such that each open set in the cover is going to cover the one facet only. So this will be like an open set. So let's take an open set here that covers just one facet. So one facet is in its interior, and it partially covers some of the other facets, but it just covers one facet. And we take the open set such that when they overlap, so for each facet there's going to be an open set covering it. But so each open set only covers one facet entirely, and it doesn't cover two facets entirely. But we're gonna say that in the middle of a facet, if you look in the middle of a facet here, so let's look in the middle of this facet. We demand that we cover, so we're gonna construct the cover. There's a lot of flexibilities for how we construct this cover, and that would be an indicator function for the cover. So so the way we are gonna construct it is we have one open set cover one facet, but at the interior of one facet, like one of those hexagons, we need a region such that this region here is at the intersection of 7 different covers, because that's possible because here this open set here can be at the intersection of 7 open sets in the cover, because there's going to be so this open set is covered by this little interior open set is covered by the open set in the cover that's covering this facet. But then there are hexagons, so there are also 6 adjacent covers that covers the adjacent hexagons, but they all have to kind of overlap a little in the interior. So in the interior, there's a region that's covered by 7 open sets. Okay, so once we construct this cover, we can see that, and then we can have this indicator function that's just that's kind of mostly 1 on each of these open sets. It's mostly 1 in the open sets, and then it's exactly equal to 1, like in a neighborhood of the facets. So with this indicator function, this infinite sum actually becomes finite sums locally. Just because each point in the moment polytope only belongs to a certain number of open covers that we have, and if it doesn't belong to open cover, then this indicator function would make that term 0. So there are only finitely many terms here. So we can see at the vertex, there will be like 3 terms. So that would be, a vertex is like a moment polytope for C3. And then at the interior of the hexagon, I keep moving, sorry. I said the very interior, there will be an open set that's in the overlap of 7 different covers. So in the interior, there will be a region where there are 7 different terms that corresponds to a symplectic reduction from C7 down to the 3-dimensional manifold. So this total space is Calabi-Yau. So locally, they're also Calabi-Yau. So in the interior, this is going to give us something that looks like the canonical bundle over CP2 blown up by 3 points. So in this interior, so that can be thought of as like the symplectic reduction from C7 to the canonical bundle over CP2 blown up by 3 points. So that's what this symplectic structure will give you. So so this is the potential, and if we take the Hessian of the potential, we get this function we call psi jk. So here I named this, so there's some notation issues. So not issues, there's just a lot of notation. So I decided to define 3 to be eta. So the C has coordinate C1, C2, and then the third component of the moment map coordinate, we decided to call it eta because it's a little different from the C1, C2 is the vertical component. So the eta component is a little special because the formulas all work a little different for eta. So we decided to call it eta, but then it's a little difficult to write down the hashing. In this formula, I just said C eta is just eta. So C3 is eta. So this is just the hashing of G for all 3 coordinates. And then dg dc gives a variable rho, and then there's this f. So if we take dg dc, there's a rho, and then there's going to be the Kähler potential f is going to be a function of the coordinate rho. Rho is actually the real part of so rho is going to be part of the complex toric coordinate. So so if we write down, so this y has the complex T3 acting on it, and the 3 complex toric coordinates are this T1, T2, T3, and then this rho is, so the real part of the complex toric coordinate is e to the rho. So here, basically f is the Legendre transform of G. So if you take Legendre transform of G with respect to C, you get a function that's a function of rho. And the hashing of f is the inverse of the hashing of G. And this is the symplectic structure that's given by the hashing of f times d rho d theta, and in the moment map coordinate, the symplectic structure is just dc d theta. Sorry, I saw that I have too little. I thought I don't need all the time, but I actually am over time. So okay. So now to talk about the monodromy, which is I think the most interesting part of our project, is that so the monodromy computation is mostly to for our need is mostly to show that the monodromy of this Lagrangian LK in the fiber around the singularity of the fibration is Hamiltonian isotopic to LK plus 1. So the monodromy is just you take a circle in the base of the fibration, and then you take a parallel transport of this Lagrangian LK around the circle in the base, and then you get something again in that fiber, and that's Hamiltonian isotopic to LK plus 1. So for us, in this mirror symmetry picture, we need this fact in order to compute the differentials between 2 Lagrangians. So when we compute the differentials, so this is used for computing differentials. So if we when we compute differentials of 2 Lagrangians in the total space of Y, that would be 2 Lagrangians corresponding to this 2 U-shaped curve in the base. Remember, Lagrangians in Y are Lagrangians in the fiber parallel transported along a U-shaped curve in the base. So yeah, so when we compute the differential for the by taking 2 Lagrangians in Y, we can see that in the base, there's a bigon between them. So, and then this bigon has two intersection points. So to compute this differential, we need to look at kind of a lift of this bigon in the total space. So there are two intersection points, and this one kind of differ from this one by like a halfway turn this way and a halfway turn this way. So total it would be like a one loop around. So so this monodromy kind of relates this intersection point to this intersection points, I think. And so just very briefly, so that's why kind of we want to compute the monodromy, because that's going to involve this is the Lagrangian that's going to be involved in our computation, but this is kind of difficult to look at. It's much easier to look at this LK plus ones. So if we can show that this Lagrangian is Hamiltonian isotopic to LK plus one, then in our differential computations, we can just only use LK plus ones and all the LKs instead of monodromy of LK around the loop. So so how do we show this? So let's think about what this parallel transport is. So the superpotential we haven't talked a lot about. So this superpotential is given by the third complex toric coordinate. So the toric coordinates are the coordinates on the complex T3 that's acting on the on Y. So Y is a toric manifold with a T3 action, and so so it's always going to be T3. So this T3 is the product of all the homogeneous coordinates. It's always going to give you T3 because this is Calabi-Yau, and locally is like a canonical bundle. So if you multiply all the homogeneous coordinates on Y, you're gonna get the T3 as the superpotential. And in the so T3 is just by definition is this looks like this, and we can write this in the action angle coordinates based on using this relation between the complex coordinates and the moment map coordinate. And so this is the superpotential, and a horizontal lift of a vector field around the circle. So if we take dd theta, which is a vector field along the circle, the tangent vectors along the circle, and if you look at the horizontal lift of this, that lifts is in the span of the Hamiltonian vector field generated by log V, norm V. So if we just calculate this, we get a horizontal lift. That's so the dv naught of this is supposed to give you dd theta. So this would be the horizontal lift, and then so because of this, the parallel transport is just given by you take this coordinates, the action and angle coordinates, and then the angle coordinate changes in this way. So these terms are what gives the monodromy, and kind of so now, yeah, so we just found that it's really easy to just like calculate what this parallel transport is and so on when we use this action angle coordinates. And then now to prove the proposition that we said earlier, we have that on a fiber. So the reason that this is true is that on a fiber, we have a Hamiltonian vector field such that the flow of that Hamiltonian vector field is going to take this to this one. So then that Hamiltonian vector field is just given by this formula. So So this formula you can get just by kind of looking at this parallel transport. You can see that if we have a Hamiltonian vector field like this, the flow of that Hamiltonian vector field for time 2 pi on this Lagrangian LK plus 1. So LK plus 1 has a formula that that tells you how the theta changes with respect to the rows. And then you use the flow of this Hamiltonian. You can see just like this is a very straightforward calculation that shows that this is equal to the parallel transport of this LK along the circle in the base. So the monodromy of LK is going to be Hamiltonian isotopic to LK plus 1, with this being the Hamiltonian vector field. And this flow is well defined on the quotient. So far it's defined on Y tilde, but it's also well defined on the quotient. And this is also just a direct calculation. You can show that it is true because the moment map is omega Z2 equivariant. So since we are using the moment map coordinate, we can use all these facts, and then it's quite easy to show that this function f j of c just defined by this. So on a fiber, this eta is a function of c. So we have this function f. So this term in the parallel transport, when we just look at the fiber, is just a function of the C1, C2 coordinates. And this function with respect to the omega Z2 action, it satisfies this identity, so that this fact will make this flow well defined on the quotient as well. So then that proves this proposition. And to end the last 2 minutes, I just want to mention one extra fact about this this parallel transport that I think is quite cool. Actually, in Catherine's thesis, she kind of used something like this to show this, but here we don't really need it, but it's still very, very fun to see this. So if we fix a positive number and we consider a region in the moment polytope. So suppose our moment polytope is like this octant that's like C3. So we fix a positive number B, and we consider this region. So we fix a facet n. So let's suppose we fix this facet n, and we fix a positive number B, and then we let this L. So Ln is the defining equation for this facet. It's just a linear equation that defines this facet. And suppose we let Ln go to 0 on this region. So Ln equals to 0 is this facet. So we are going towards this facet, but in this region. So in this region means that we are kind of some distance away from all the other facets. So by this bound B. So we are not going close to the other facet, but we are going close to this facet. Then this term in this parallel transport approaches this minus n1, minus n2, which is the inward normal in the 2D projection of this moment polytope. So you can see that the inward normal, the first two components of the inward normal is given by minus n1, minus n2. Okay, so that's just a fun fact. Yeah, I can end there. Thanks.
Great, thanks so much, Heather, for the great talk. Let's give her a round of applause. So are there any questions for the speaker?
Yeah, I have a question. And I don't know if I should ask you or if I should ask Catherine, but I'll ask you and then you can. Did you every genus 2 curve is hyperelliptic, has an evolution whose quotient is an elliptic curve. Did you think about what this says about the relationship about this mirror statement and what is known for elliptic curves?
Oh, that I've never thought about. What about you, Catherine?
Which involution are you
Well, so
about?
this is some. I mean, I think I'm not lost. So you're studying the genus 2 curve on the B side.
Yeah, that's right. Yeah.
And so one of the statements that comes out of understanding the moduli space of genus 2 curves is that every one of them has at least a Z2 worth of symmetry. At least it has a holomorphic involution. And that holomorphic involution, I mean, it's its quotient is not going to be an unbranched, but the quotient is some kind of branch cover. Everything one of them is a twofold branch cover of an elliptic curve. And so what I was wondering is whether, in the course of this, apparently the answer is no. In the course of this project, whether you thought about so that would suggest that there is some automorphism of the Fukaya category of this mirror side, so that if we studied this automorphism and we looked at somehow some quotient category, we would be able to see Fukaya categories of tori. And so therefore it makes it, at least to me, natural to just wonder whether that automorphism is geometric, whether there is some symplectic topology going on here. It's only because somehow, when Catherine proved her result, I just thought, well, this genus 2 curve, and she proved something in some kind of neighborhood of infinity, but now you have something global. So I can start asking questions about really moduli of genus 2 curves, and this is the first one. And then, of course, there's going to be a whole list of other questions, like, probably my favorite, the one that I really wanted to ask if the answer was positive was like, there is one very special genus 2 curve with basically the octahedral group of automorphisms that has 48 different automorphisms. And so it's a genus 2 curve with a lot of symmetries. And so I can't kind of understand, I can't do the construction in my head, but I was curious kind of what is the symplectic form that has all this special symmetry. But again, that's what presumably is some kind of more complicated question than the one about just hyperelliptic curves always exist. Yes, Denis?
So I think I have an answer to your first question. The hyperelliptic involution is geometric because these mirrors, they have two vertices, right? You have these quotiented hexagons, and the hexagon you can just rotate by 180 degrees. And this is the hyperelliptic involution, up to maybe some twist by a line bundle or something. But what you should be doing is the 180-degree rotation of this thing.
And so somehow
you'll note that the key geometric structure you see in there is the three edges, right? You fold the hexagon really into a banana configuration, and what will happen to your banana configuration under this 180-degree rotation is you will swap the two triple points.
Yep.
And so that's kind of mirror to the hyperelliptic involution, which if you decompose a genus 2 curve into two pairs of pants, you switch the two pairs of pants. So that's my conjecture on that.
That would be a very appealing answer.
Now, about further symmetries. So the curve in Catherine's thesis is more symmetric in that all the areas are equal. So this one has a, I don't know what, S3 or something. Anyway, it has some extra symmetries because which is lost here if you go to the general case. Of course, the goal is to go to the general case. I suspect, though, that the one that you mentioned that's even more special does not have a mirror in this construction because rigid things tend to not have S-Way-Z mirrors. Secretly, this is only about families of things. I mean, you specialize at complex points, but this is only for things that admit large complex structure limits. So an example of that is for elliptic curves, the elliptic curve with complex multiplication, say with I or the hexagonal one, we know that there's something different about their Fourier categories that cannot be captured over the Novikov field.
Right. Well, maybe we should do this in discussion.
Yeah.
So how do those things change the complex structure again? Like
So, sorry, may I say something? So, I mean, your genus 2 curve with a large symmetry correspond to some point in the correspond to some omega, right? Right. So we can find it.
yeah, I think we do all the complex structures, not just the large ones, because when it gets too large, we change to a different chart.
That was my understanding. I mean, that was my understanding of what you proved, that somehow you really covered the entire moduli space, which is why I asked about this very special one.
Right, so your very special one, if you can, yeah, okay, maybe we can, if you can tell us where it is in the upper half plane. It has a particular period metric, right?
I certainly don't think I could tell you off the top of my head right now. So,
Okay. I think we can know how the tau changes with whatever you were mentioning, then we can figure out the omega.
Mhm.
Like what.
No, that's a good point, actually. Yeah, it has to be there in your construction, but then I would have to guess that some of its automorphisms will be very far from being geometric.
Yeah, that I agree.
Yeah.
If all is different, then it should, like, are there any automorphisms that don't change the complex structure?
Oh, yes, but thank you for the question. We should try to answer.
The only thing I'll add one more thing, which is that there's also a classification of, as far as I remember, a classification of real automorphism. I mean, anti-involutions. So when the curve is defined over R, there's we understand what happens. I think it's understood kind of what happens. And that was the other question I was going to ask, which is maybe harder to see, which is related to what Denis was saying, which is if you take the complex curve with elliptic curve with complex multiplication, sometimes it's difficult to we don't exactly do a very good job of understanding what the mirror to that is. It seems to be some phenomenon that's not entirely about symplectic topology, more about the coefficients with which we do Fukaya categories. But I suspect that at least the actual automorphisms, there may be something there, even if they're not actual symplectomorphisms. Maybe they're interesting Lagrangian correspondences, something that would be one thing to explore. Anyway, thanks for the talk. I enjoyed it.
So Mohammed, can you say again what was the group of symmetries you're talking about?
Sorry, what was the what?
What was that group of symmetries you were talking about?
It's the group of symmetries of an octahedron. But I think I mean, there are like papers just about listing all possible automorphisms of genus 2 curves. Unfortunately, if you read them, they don't tell you, they're not very good at telling you like the geometry of this group. They just give you like presentations and relations. So then you have to kind of, figure out a little bit like what could be some meaningful geometry to kind of, basic. I mean, these groups are all basically, geometric automorphism groups of, polyhedra. So in this case, it's the octahedron.
Mm-hmm.
Are there further questions for Heather? If not, why don't we, I'll stop the recording. We can head into the discussion session. So let's thank Heather again.